Hello and welcome back. We're going to finish up our discussion about the central limit theorem using sampling distribution models for means. So here we have a question. If you get on an elevator, you probably see it'll claim limit 10 people or 2,500 pounds. It's something we would see pretty often. The question we have is what is the likelihood that a random sample of 10 people would actually overweigh 2,500 pounds? So which one is more likely, the 10 people being the limit or the 2,500 pounds being the real limit? And that's kind of the question we're asking here. So also you got yourself a nice little elevator meme that I won't read to you because you're already laughing, I know. All right, so the CDC, I get this going. There we go. In 2004, the CDC reported the mean weight for adult men to be 190 pounds with a standard deviation of 59 pounds. So we're going to just focus in on men. So what is the probability that a random sample of American adult men that have an average weight of 190 pounds with a standard deviation of 59 pounds, what's the probability that that sample of 10, that random sample of 10, is going to overload the 2,500 pound limit on the elevator? So the first question we might ask is, do we expect the distribution to be skewed? So thinking about the population of all American men, would we expect that to be a skewed distribution? Or would it be unimodal and symmetric like a normal bell curve? So if you look at the graph here, this is actually, I got this graphic from the waist size, but those two are pretty closely related to each other. So on this one, we would expect it to be skewed to the right, because if we look, the average is 190 pounds, so I'm definitely below average. That's okay. And then 59 pounds is a standard deviation. So that means within one standard deviation, we'd expect 68% of men to be anywhere between 131 pounds, which is definitely on the low end, and 249 pounds. So as a fully grown adult male, can you really be much less than 131 pounds? So that, you're going to kind of get a lower end limit there. You're going to have a hard left bound on that side, right? Over here. But can you, as a fully grown adult male, American male specifically, can you be more than 249 pounds? Well, absolutely you can. You could be 2 standard deviations or possibly even 3 standard deviations. So what we're trying to say here is that the distribution in the population is going to be skewed to the right because you can always get bigger, but you get to a point on the left bound over here where you have a hard left bound and you really can't get much smaller than 131 pounds. So our population is skewed. But if we remember from the central limit theorem, it doesn't matter if our population is skewed. We can still draw sampling distribution models that will approximate be approximated well with a normal model as long as our sample size is large enough. And by large enough, it could be as small of a sample size as 2 or 3, depending on how nearly normal the population started out. So back to the question, a limit of 10 people or 2,500 pounds. So the question is, what's the probability that a random sample of 10 adult American men would overload the elevator? So if our population, so that would be if we just sampled one person, the mean for that population is 190 pounds with a standard deviation of 59. So if we had a sample of 10 random men, they would have to be greater, the average would have to be greater than 250 per person, right? So if there's 10 of them, we just do 2,500 pounds divided by 10. So their collective average of the 10 men in the sample would have to be an average sample, or a sample average of more than 250 pounds. So what's the probability of that occurring? And that's a question that we can actually answer because of the central limit theorem. So this is where our sampling distribution model comes in. So I'm going to find the sampling distribution model where n is equal to 10. So we have a sample size of 10 American adult males. So the standard deviation of that, first of all, that sample we would expect on average to be about 190. So it's going to be centered at the exact same center as the population itself, which had an average of 190. So the sample of 10, on average, we would expect most of them to be close to 100 or 190, or the most common one would average of 10 would be 190 pounds. And then the next question is, well, how far is the spread to the next standard deviation going up and down? Well, that is given by our formula, where we have the standard deviation for our sample is going to be equal to, for the sampling distribution model, is going to be equal to the sigma, which is from the population, which is 59 pounds, divided by the square root of n. And we've already talked about this square root of n business being like the law of diminishing returns. So it's an indirect relationship, but it doesn't grow as fast as we want because it's the square root of n, not just n itself. And I've shown that to you last unit. So I think I got rid of that graphic, but I'll show it to you again sometime. Anyway, whenever we put that in the calculator, so I'll do that real quick for you. So we've got 59 divided by the square root of, so I'm going to hit second, x squared, so the square root of 10, which doesn't have it's not a perfect square, so it doesn't come out even, but that's okay. It's going to be 18.65, so I'm going to round that just to 18.7. So our sampling distribution model for the sample of 10 adult American males is going to be centered at 19 with a standard deviation of 18.7. And remember, that goes in both directions, right? So then the question is, what's the probability that the sample would be larger than 250 pounds? Well, if we look here, how many standard deviations would I have to go over before I get to 250 pounds? This is going to be way out here. So whenever we find the z-score, the observation minus the mean divided by standard deviation, it's 3.2 standard deviations. So what's the probability of that? Well, we can find that. It's not even showing up on our model, is it? By going to, let's see. So it's in the distribution menu. So second, variables, distribution menu. And we're going to take the normal CDF, which is the cumulative density function. So it's like an integral. We're finding the area under the curve. Our lower bound is going to be 250 with an upper bound of, we can do 999, but if we went to 300, that would be more than enough, right? Centered, we're not using z-scores, or we could because we do have a z-score, but we're going to use the actual values. So centered at 190 with a standard deviation of 18.7. We hit paste, and the probability of that is 6.6 times 10 to the negative fourth power. So there's 3 zeros in front of that. So if I write that out, it's going to look something along the lines of this. So it's going to be 0.0006, I think it was 6, right? And that's going to be the probability of that occurring. So that is well less than 1% and well beyond 2 standard deviations. And so that would be a very, very unlikely and an unusual observation if we had a random sample of 10 men that had an average of over 250 pounds, meaning combined they weighed over 250 pounds. So which one is more likely to occur? To have a limit of 10 people that could fit into the elevator, or to reach the weight limit? So the space limit of 10 people, or comfortably, or the weight limit of 2,500 pounds. Well, obviously, the number of 10 people is going to be more probable than that. So kind of a cool question. So what did we just do? Well, this is all basically modeled out here by the fundamental theorem of statistics. So our population, which is our distribution here of men's weight, it started out slightly skewed to the right. Now, not horribly skewed to the right, but still skewed to the right. Not like CEO data or CEO compensations. That was way skewed to the right. We had to use logarithms to fix that one, right? All right, then sample distribution. So from this population of American men, we take a bunch of samples of 10. So here's a sample of 10 men, here's another sample of 10 men, and another sample of 10 men. Now, by themselves, the sample distributions, they reflect, they're like little mini populations, right? They're little representative samples of the population. So they also are going to be skewed. So how does it become more nearly normal? Well, it's not the sample distributions that become normal, but when we put those averages together, so the average of this 10, which looks to be on the kind of the lower end because you got more here. This one seems to be kind of more towards the middle. This would have an average on the lower end. And then here, this one also might be a little bit on the higher end. So when we put all those together, those averages, we end up with the sampling distributions put together, which gives us a model that becomes, as we increase our sample size, would become more nearly normal, which can be approximated well by the sampling distribution model, which is lovely, with us centered at the population mean, which was 190, with a standard deviation of the standard deviation of the population divided by the square root of n. So it does decrease with the law of diminishing returns, but it does decrease as we increase our sample size. So that's basically the whole process of what we're doing with statistical inference, and it's all powered by the fundamental theorem of statistics, or the central limit theorem. And central is telling us that it's the central idea of statistics, not that central as in like an average or a mode or something like that, or a median. So here's some more, just a review of central limit theorem in action. When we had a population of 1, when we just rolled 1 dice, it was unimodal. We're just as likely to roll a 1 as we are a 6. But when we take the average of a sample size of 2, which is a 2 dice average, now we start seeing this triangular distribution, which already becomes much more nearly normal, even when we increase the sample size from 1, our population, to 2, with this is a 2 dice average. And as we increase the average of the more dice, right, as a 3 dice average, now it's even more nearly normal, right? I'm pretty comfortable with using this. Even a small sample size of 3 to approximate the sampling distribution model with a bell curve. But as we go to a sample size of 5, this looks really, really close, even more close than this one, right? And as we increase the number of dice that we're taking the average of, we're going to get closer and closer to a smaller and smaller standard deviation, but always still centered at 3.5. Notice how all of these are centered and have an average at 3.5. So that's the central limit theorem in action. Here's another one. Even what's really powerful about central limit theorem is even when the population itself is heavily skewed. So this is when we have a sample size of 1. So n is equal to 1, right? That's the population. If we sample just sample sizes of 1, we're just sampling the population, right? Or our sampling distribution would be the population at that point. So it would still be skewed. But as we do a sample size of 30, now why do we have to use 30? Well, it's because this is so heavily skewed, right? So if we take an average of just 2 people, right, and we get one of the really, really big companies, CEOs, that's going to be very heavily skewed by that 1. But if we take samples of 30 companies and we just so happen to get the Walmart CEO or something like that, it's not going to have as much of an impact in skewing our mean as a smaller sample would. And that's the whole point here. So as we do that, this is going to have a true average, right? And all of these are going to be centered at those averages as well. And if you notice, that's pretty cool because they're all centered at that same average. But the difference is that the standard deviation is going to shrink, and the graphs are going to become, or the sampling distributions are going to become more nearly normal as we increase our sample size. So starting at a sample size of 30, it looks fairly normal, but it's kind of cut off over here and skewed to the right, right? Still also cut off and skewed to the right, just like the original population when we have a sample of 50. So because this is so skewed, we need to have a large sample, like maybe 100, or even better, a sample size of 200. So if we really wanted to approximate or use inferences using this population with a sampling distribution model for the averages, or try to estimate something like that, we would want to take a sample size of 200 of those 500 companies, which is pretty large. At that point, you've totally violated the 10% condition, because you wouldn't be sampling with replacement. So yeah, we really couldn't go any higher than the 50 on this case, because it is the Fortune 500, right? The top 500 grossing companies or something like that. I don't know. I'm not an economist, or I don't even know how to say it. I don't do English very well either. I just like numbers. All right. So waist size. So this is actually the same graphic that I used for the weight, because those two are pretty closely related. But with waist size, again, you can only get so small, but you can always get bigger, right? Especially in America. Thinking of like giant jacked up trucks or something like that. All right, so our population is slightly skewed to the right. Sample size of 2 here is still slightly skewed to the right, but because our original population wasn't heavily skewed, even a sample size of 2 is going to be almost normal enough, right? So we might be able to get away with using a sampling distribution model of samples of average of just 2 adult males. All right, sample size of 5 is even better. 10 is better. 20 is better, of course. But by the time we got to 5 or 2, we would probably be good enough. So we used to have a condition with proportions, the success failure condition, where in order to guarantee that we had 3 standard deviations that were uncut off by a hard bound of 0 or 1, we had to have at least 10 successes and 10 expected failures. We were able to actually adjust that depending on our p-value. Remember, we got it down to 4.5, but you don't need to know that. If our p-value, I think, was 0.5, yeah, we could have as low as 4.5, which would be a sample size of 5, by the way. But that's extra stuff you don't need to know. Just kind of cool. But in this case, what is large enough? There's no rule like golden rule like 10, which would guarantee 3 standard deviations. So you just have to think about how severely skewed the data is. So when we started out with the Fortune 500 companies, we need a really large sample of probably around 200, right? But when we're doing waste size, we could have got away with 2. So that would have been large enough. So it just depends on the context. All right, so that's it for the lecture today. We pretty well finished talking about the central limit theorem and sampling distribution models for means. So at this point, if you get out your assignment, if you have it printed out, that would be great. If you don't, you can just copy it over on another sheet of paper. Again, keep in mind that the odd questions are in the back of the book, so you can check your answers as you go, because I won't be able to really provide feedback at this point. So sampling distribution models, well, let's look at the difference between the sampling distribution model for proportion, which is up on the top, for categorical data, and sampling distribution models for means, which is using quantitative data. So when we are dealing with proportions like success or failure, heads or tails, yes or no, approve or disapprove, that's categorical data, failures and successes, probability of success 20%, right? And the standard deviation of that, because it's based on the binomial model, is tied to the probability of success and failure. That's what tells us how far it is skewed to the right or to the left, or the standard deviation. That's all pretty well accounted for by just knowing what the value of P is. But when it comes to means, each population, regardless of what its mean is going to have a different standard deviation, right? So we have to just take that into account by using the standard deviation from the population in our formula. Now, notice the similarities between these two formulas for the sampling or the standard deviation for both sampling distribution models. Both of them are divided by the square root of n, and in this case, the square root of n as well. So they're both decreasing the standard deviation of the sampling distribution model by the square root of n, which is that law of diminishing returns. Fundamental theorem of statistics, we talked about that quite a bit. Regardless of what our population looks like, whether it's skewed, multimodal, bimodal, unimodal, or anything, it doesn't matter, or even really heavily skewed like this one, the sampling distributions will look like little samples of that. But when we put the averages of these samples together, it becomes more nearly normal, centered at the same mean as the original population, and can be approximated by a sampling distribution model using the parameters of mu and sigma divided by the square root of n for the standard deviation. All right, so let's work the two examples, the even problems that are not in the back of the book, and then on the back side of the assignment, you can do the odd ones on your own and check your work. So 44 is about rainfall. It says stats from Cornell's Northeast Region Climate Center indicate that Ithaca, New York gets an average of 35.4 inches of rain each year with a standard deviation of 4.2. Assume that the normal model applies. So the reason we have to assume that the normal model applies here is because the first question is actually based on the population. So we're assuming that the population is unimodal or symmetric. We wouldn't have to assume that it was unimodal or symmetric if we were using a larger sample than just the population sample size of 1. Okay, so first part A says, during what percent of those years does Ithaca get more than 40 degrees of rain? So I graph this out. This is the average, right? One standard deviation is here. We want to know what's the percentage of the years that Ithaca get more than 40 inches of rain. Well, that's going to be more than 4.2 standard deviations, 4.2 degrees inches. I'm sorry, it's late. 4.2 inches above this, more than 1 standard deviation. So it would be something about right there. That's just an approximation. So we want to know what percent of years do they have an average annual rainfall larger than that value. So graphically, it would look something along the lines of that. Don't you love those graphics? That's kind of fun. So we want to know what is the probability or the area underneath this curve. Well, to do that, we go back to our CDF, cumulative density function. So I'm going to press second variables to get to distribution menu, normal CDF. The lower limit is going to be 40 inches of rain. Upper limit, we'll just do 99 inches. That'll be plenty of standard deviations of z-scores, right? So centered at 35.4 with a standard deviation of 4.2, and then hit paste. So it looks like the probability of having annual rainfall in Ithaca and on any given year it's going to be 13.6%, or you can round 13.7%. So what percent of years have less than how much rainfall falls in the driest 20%? Okay, so now instead of giving an actual value and then finding the probability of that, we're going a statistic or whatever. We're going to start out with the probability and try to find the appropriate observation for that one. So the driest 20%. Well, I know 68% is in the middle using the empirical rule, so that would leave 32% on each tail, so that would give me 16% here. So the driest 20% is just going to be a little bit less than 1 standard deviation below the mean. So even if you didn't know that, that's just to graph this out. So let's find out what that exact value is. Well, we're working backwards now, right? We're trying to find the area under the curve. Or sorry, we started out with the area under the curve, and we want to find what's the statistic or the observation that's associated with that value. So we want to know, where is this located right here? So how far in an actual value? So when we put that in the calculator, go to second, variables to distribution. We're going to do inverse normal. So inverse normal. The area under the curve is going to be 20%. Center, we don't want a z-score, so we're going to use our actual parameters. So 35.4 with a standard deviation of 4.2. Now the tail, this is nice on newer models. We're going to go from the left. Usually the inverse model defaults to the left, but sometimes we like to do from the center when we're doing confidence intervals. We want to find the critical values, or sometimes we even go from the right. So we're going to draw our region or our area. Notice how this is, the bound is coming, it's being drawn out from the left. I'm going to go down to pace and hit enter. So that tells us that it's going to be 31.8 inches of rain. So the driest 20% of years have less than, so let me see if I get that, less than 31.8 inches of rain. And that's how we solved it. Now, nothing we did here actually involved the central limit theorem, because we're just dealing with the population, 1 year, right? Sample size of 1 year. But on the next two problems, now we're going to be looking at for 4 years. So the average rainfall in the 4 years. So Cornell University student in Ithaca is in Ithaca for 4 years. Let something represent the mean. There's a typo there. Let something represent the mean about the mean amount of rain for the 4 years. Describe the sampling distribution model for the sample mean. All right, so we're going to take the 4-year average while they're in college. So assuming those years are independent of each other and they're all random samples, what would the population or the sampling distribution model look like for an average for a sample size of 4? So now we're not just looking at the population, we're looking at a sampling distribution model with a sample size of 4 years. Now it's still going to be centered at the same average of the population, which was 35.4, but now our standard deviation is going to be smaller. How much smaller? Well, it's going to be by the square root of n, right? In this case, n is 4. Square root of 4 is going to be 2. So it's going to be half the standard deviation of the last one, right? So if our population had a standard deviation of 4.2, we know this one will have a standard deviation of 2.1. So this was a nice number to work with because it was a perfect square. But if it wasn't, you just put it in the calculator. But I'm going to skip that step. Yeah, because we'll probably end up doing it on the next problem. So I'll just skip it on this one. But you just put it in the calculator. All right, so we want to know what's the probability that those years average less than 30 inches of rain. So 30 inches of rain, we know that's going to be more than 2 standard deviations. If we do a z-score, observation minus the mean divided by standard deviation, we know it's 2.5 standard deviations below average. So the area under the curve would look something along the lines of that. We want to know what's the probability of that occurring. So what's the probability the random sample of 4 years has an average less than 30 inches of rain. So not any 1 year being less than 30 inches of rain. That would be the previous problem because we would be talking about the population. But if an average of 4 years or 4-year average is less than 30, now we're talking about the sampling distribution model with the sample size of 4, which has half the standard deviation of the population model. Okay. And because the central limit theorem, even if the population was not normally distributed, we probably, as long as it's not heavily skewed, we probably would be okay with using a small sample of 4 and can use the sampling distribution model using a bell curve. So how do we find that probability? Well, we just put it in our calculator. We're finding the area under the curve. So we're going to go to second variables. I'm going to arrow down to the CDF. Our lower limits in this case is going to be negative infinity or 0 inches of rain. You could even do that. We'll just leave it as it is there. Our upper limit is going to be 30 inches of rain, centered at 35.4, which is the same as the population, with a standard deviation half as big of 2.1, which gives us probability of 0.5%, or 0.005. So what's the probability that the 4 years that he's in school, they have an average 4-year average of rain less than 30 inches of rain? Is going to be 0.5%, which would be very, very rare. And because it's further than 2 standard deviations from the mean, we would consider this an unusual observation. All right, 54, potato chips. The weight of potato chips in a medium-sized bag is stated to be 10 ounces. The amount the packaging machine puts out in the bags is believed to be have a normal model. So again, they're telling us that the population is normally distributed. We don't actually need to know that unless we're using, like we are in this one, a model for the population with sample size of 1. If the model was skewed or bimodal or anyway not normal, as long as we have a large enough sample, we can still use a sampling distribution model. Again, that's the power of the central limit theorem, or the fundamental theorem of statistics, is that it becomes more nearly normal as we increase the sample size. All right, with the mean, so the actual average is more than what they state. So they state it's 10 ounces, but they actually overfill it on average, which is to avoid lawsuits. All right, and standard deviation of 0.12 ounces. So what fraction of all bags that are sold would be underweight? So in order to find that, so the 10 would be, anything less than 10 would be underweight. So we're looking for the area underneath the curve here. Notice this is not a sampling distribution model. We're talking about a single bag. So this is just the population itself. Again, they had to tell us it was normally distributed. Otherwise, this would not be appropriate. So to find the area under the curve, all we have to do is... we'll put that in. Again, we're going to go to second variables distribution menu. We'll go to the CDF. Negative infinity, our upper bound is 10, centered at 10.2 with a standard deviation of 0.12 ounces. Alrighty. So they're saying about 4.8% of all bags would be underfilled. So, if they had lawsuits, I guess that would be 4.8% of people would be pretty upset about that, right? They're probably not worried. It is just a bag of potato chips. I don't think our alpha level needs to be that strict. All right. So the observation is 1.67 standard deviations below the mean. So it wouldn't necessarily be considered unusual because it's less than 2 standard deviations from the mean. So some of the chips are sold in bargain packs of 3 bags. What's the probability that none of the 3 is underweight? So if we know that the probability that one of them is underweight, we'll say is 5%. We're just going to round up to make the math easier. Then what's the probability that none of them are underweight? Well, if we look here at our tree here, our tree diagram, what's the probability that the first one, these are independent events, right? That's an independent sample, unless they were all packaged at the same time and there was a malfunction where they all were underweight, or then each one would not be independent, right? So it is an assumption. Independence is always an assumption. All right, so in this case, what's the probability the first one is not underweight? That would be 95% of the bags are not underweight. And then the second one not being underweight would be 95% as well. And then the third one not being underweight would be 95% as well. So to find the probability that we have not underweight, not underweight, and not underweight, that would be 0.9 to the third power. So we'll do 0.95 caret, if I can get to the caret button. I wonder if it'll work on my keyboard. Oh, nice. That's awesome. Caret 3, which will give us an 85%. So the probability that we don't have any of those 3 from our bargain pack being underweight is 95.7%, which is going to be most people, right? All right, C. What's the probability that the mean weight of the 3 bags is below the stated amount? So not that any one of those bags is below the stated amount, which would be a 5% or 4.8, which is what we said. But what's the probability that the average of the 3 bags is less than the stated amount? Which would mean that 2 of them would have to be underweight, or 1 of them would have to be like way underweight in order to skew that mean to be below the actual average. And well, below 10, because the actual average is here. So the probability of that's going to be pretty rare. In fact, our standard deviation here is going to be less than the original one of 0.12. And now it's because it's a sample size of 3, a standard deviation is being divided by the square root of 3. So if we put that in the calculator, and I'll do it proper this time, I'm going to put it in as a fraction. So if I hit alpha x, if it's updated to the latest software or the latest update, it'll actually do that function for you, which is kind of nice. All right, so in the numerator, we have the standard deviation of the population, which is 0.12 divided by the square root of 3. So I'm going to do it just like that. Okay, don't really have to do that. So essentially, we get 7 or 7% of an ounce, which is kind of a weird unit to think about, but that works. So it shrank, but not by much because it was just a sample of 3. But it does shrink pretty aggressively at the beginning, but then we have the law of diminishing returns, right? Just look at the graph of the square root of x. All right, so the z-score for that was less than or more than 2 standard deviations from the mean, so it's the very small area here. You can barely even see that shaded in. I don't know why I went through all that effort then. So all I have to do is put it in the calculator at this point to find the actual probability of that. So we'll do second. I'm trying to play out the fact that I totally had an Irish accent for a moment there, but it's okay. Okay, normal CDF. I know there's some words I say, like standard deviation, that sound very Irish. It's kind of fun. Lower, upper, centered at, we said 10.2. I don't know why I changed that. Our new standard deviation is 0.07. There, I did it again. Okay, and hit paste. So the probability that the 3 bags have an average weight that's less than 10 ounces, the stated amount, is only going to be 0.2%, which is very, very rare, of course. And it's more than 2 standard deviations below the mean, so of course it would be considered an unusual observation. All right, last question we have here. Let me check that. Yeah, it is the last one, is part D. So now we have a larger sample, a case of 24 or 24 bag case of potato chips. What's the probability that the mean weight of that is going to be 10 ounces below average? Well, when we have such a large sample, 24, having not just one of them, but a majority of them are so skewed to the left, that we would have an average of 24 less than 10 ounces is going to be very, very rare. And it should make sense that it's going to be more rare, right? So in this case, when we crunch the numbers here, we end up with a standard deviation, it's divided by the square root of 24, which is close to the square root of 25, which is about 5. So it's a fifth of standard deviation. So the probability of that occurring is going to go down drastically as well. In fact, now we're going to have a z-score of -8 standard deviations below the mean. So if we count over 1, 2, 3, 4, 5, 6, 7, 8, like way, way over here. Obviously, that's not going to show up on our little sliding thing here. So, oh, it did show up. You're not supposed to see that. Now you know my trade secrets. So it is -8 standard deviations below the mean. If we put that in the calculator, it's going to give us practically 0. We're just going to have so many zeros in front of it, it's not going to be significant. So for all likely purposes, the probability of that happening is it's not going to happen, which is not very precise, but you get the idea. Be highly, highly, highly unusual. All right, so you can do the last 2 problems on your own. Again, the answers are in the back of the book. They're really similarly worded to these 2, so if you need to go back and look at the problems and how we solved them again, there's some beautiful graphics in here, especially showing the whole process, like right here. Yeah, so really try to quiz yourself and make sure you understand, what is this whole central limit theorem all about? What's the difference between using inferences with proportions and using inferences with means? So let me see if I can pull up that slide. Right here. Yeah, so we did inference with proportions and sampling distribution models. This is our standard deviation for the sampling distribution model. But whenever we do the sampling distribution model for a mean using quantitative data, like waist size or average weight or anything like that, or ACT scores even, or average ACT scores, Now we're dealing with the standard deviation of the population, which is of course different from population to population, not tied to P and Q because it's not tied to the binomial model. We're not talking about just flipping coins or anything. We have different varying, like CEO data, of course, because it's skewed to the right, it's going to have a huge standard deviation, where something like waist size is going to be much smaller because it's more nearly normal. And even if it was more nearly normal, there's still, flatter curves and there's taller curves, to use the words that they use in the news right now, right? So that's a square root, and both of them in common are divided by the square root of n. So we have that law of diminishing returns there.